Hello viewers, welcome to Coding Interviews channel. Hope you are doing great. If you haven't subscribed to the channel yet, please go ahead and subscribe. I have created bunch of playlists to cover various categories of problems such as BFS, DFS, dynamic programming, stacks, queues, linked lists, trees, graphs and so on. Please check them out. I have uploaded the code for this problem to the GitHub repository. You can get the link from description below this video. Let's jump into today's problem. Word search 2. Given a 2D board and a list of words from the dictionary, find all words in the board. Each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are those horizontally or vertically neighboring. The same letter cell may not be used more than once in a word. So we are given with a two-dimensional board basically, so that has all the different characters, right? And we are given with the words in the dictionary, right? So now we need to find how many of these words can be formed by using the characters in the 2D board, right? So if you look at the example, right, on the left side, so this is a 4x4 board, two-dimensional, and it has given like word oath, pee, eat, rain, right? So these are the 4 words. So now we need to find how many of these words can be formed by using the characters in the board. So how we are going to select the characters is we have to select only if they are adjacent, right? So adjacent means they could be horizontally connected or vertically connected. So the connection here means they should be next to each other, right? So for example, oath, right? So OATH, right? So the characters which are coded in sort of orange color, so they form the word oath, right? So for example, right, if you are looking for PEA, right? So in fact there is no P in this particular board, right? So you have E and A, but there is no P, right? So that means you won't be able to form this particular word, right? So there are two things that we are trying to solve here. So first thing is you need to go through these characters by following the rules of horizontally and vertically connected, right? And those words should be existing in the words, right? So for example, a hat, let's say a word called hat, right? HAT, right? So if you don't consider the adjacent property, right, you could actually make hat with the words and with the letters given here, right? There is H, there is A, there is T, but can we construct the word hat by following this adjacency principle where the cells must be horizontally or vertically neighboring? So first H should be there, we can find H. And A, do you have A which is directly connected with H either horizontally or vertically? No, not really. So that means hat cannot be constructed, right? Cannot be found basically. That's what we would say. So that's the good use case that we need to iron out, right? So basically the number of words, if you look at in this example, right, there are just only 4 words and here there are 16 characters, right? So in each word you have multiple letters here. This word is starting with O, this word is starting with P, E and R, right? But there are so many characters. That means we have to minimize our search to only these starting points, starting with O, starting with P, starting with E, starting with R, right? So that's one thing. So how can we make our search is starting with only these words, not, that means you want to avoid all the words, for example starting with H. So I don't want to start my search with H, I don't want to start with my search with K, I don't want to start my search with V, right? So likewise, I don't want to search for the things which are not there in the words. So that is one constraint. So that is to start with only first character. So what if we move our needle to the second character also, right? So I have some examples here. So we don't want to search for characters OP, let's say, or EI or RE, right? So R can be found, E can be found, but we don't want to search with RE. We only want to search for RA, right? Because that is what is there in the words, right? For example, right? So even though R and E are adjacent here in the board, we don't want to search in that path because RE is not there, not even there in the words list, right? But RA is there. But in fact, RA, there is no A adjacent to it. So we don't have to go further in searching after we found R, right? That means at every step, what we are trying to see is, okay, do I want to go in that particular path or not? That kind of decision we are trying to make, right? So that we are trying to minimize the search space, right? So how can we make sure whether these prefixes, I'm going to call them as prefixes, right? So if you are looking for the first letter, right, O, P, E, R. So this O is a prefix for word oath, P is a prefix for word P, eat's prefix is E, right? So that is a single character prefix, right? So for all those different prefixes, we want to make sure they are existing in this word. Then only we want to proceed further. So when we found O, right, we want to make sure there is a word with prefix O. Yes, there is a word. When we encounter A, O plus A, right, OA. So we want to make sure there is a word with prefix OA. Yes, it is still there. OAA, if you move like horizontal direction, do we have a word OAA starting in words? No. So we don't have to go that path. So we go down, OAT. Is there a word? Yes, that prefix is there. OATE, let's say OATE, right? So is there a word like that? No, we don't have to go that path at all. So like that, we want to minimize our search space, right? So we don't want to do unnecessary searches, right? But how can we make sure these valid prefixes are available in the given set of words, right? So that is when, if you start looking into straight away comparing the strings and coming back with, okay, these are the prefixes are there in the words, right? That will be time consuming with the simple string searching, right? So for that purpose, what we could do is we could employ a data structure called a try data structure, right? So I have extensively made another video for the try data structure. I have put the link for the try data structure and overview of that video, overview of try data structure in separate video, and you can get the link from the description. So you can pause this video right now here and watch the try data structure video so that it will be easy for you to solve this particular problem. So because we are going to use a try data structure for solving this problem. So please go ahead and watch the try data structure video so that this problem will be easily understood to go forward, right? So just to recap, right, try is a data structure which will enable us to search various strings. Basically, you can call try as a prefix tree also. So since we are dealing with prefix search here, right, so try data structure is appropriate for this particular problem, right? So first of all, what we are going to do is we will be building a try data structure for all these words, okay, so that whenever you go through this board, you will see if that prefix is there in your try data structure. If it is there, you go down through that search path. If it is not there, you don't even go through that search path, right? So that's the idea. So to enable that idea, we are going to use the try data structure. Again, I highly recommend you to watch the try data structure video that I have put in the description section of this video. Come back and watch this video again, right? So what we are going to use in the try data structure is, there is one additional method that I have here. So in the other video you would find two methods, basically to insert a word into try data structure and to search a word in the try data structure. So in this particular code, whatever I am going to show you, it will have a new method called prefix exist. Basically you are going to search for a prefix. In addition to the insert and search, I have another method called prefix search, which we will walk through, right? So to just give you how the try will be looking for us, right? So let me insert this into try data structure, right? I will have A, right? Next I will have T, next I will have H, right? So this is what I will have in terms of oath that I have put in, right? And next, so here in these words, fortunately the words are all having different start points, right? But what if they have similar start points? Let's say you have oath here, right? Let's say you have another word called onto, right? So that means you will have N, right? T, right? Likewise. So likewise we will be forming the try data structure, right? So once you form the try data structure, so this is basically the insertion, right? What you are going to do is the search. So let's say our try has only these two words, right? Oath and onto. So our try has oath and onto, right? So now search for P. What we are going to see is, okay, whether the first character, whether you have P starting. No, we just say no, I don't have it. We search it, right? But for example, you are searching for the prefix called O. We will say, okay, true, right? Because we have this. Search prefix for ON. Yes, we do have a prefix for ON, right? So likewise the search will become easier for us. So before diving into the problem, let's go ahead and look at the try data structure, right? So let me minimize this. Okay, so this is all similar that you have watched already in another video, right? So we will have 26 child pointers because there are lowercase letters from A to Z. So A to Z we have 26 letters in English, that's why we have 26 child pointers, and all of them will be initialized to null. And we have another pointer called word end, which is initialized to false. Again, this is all we have already covered if you would have already watched the video that I mentioned, right? So, and this method is about inserting the word into the try data structure, right? And this is again search for a given word, right? These two methods should be similar to whatever I have shown in other video, right? And now this is the new method that is used for this problem solving, right? So prefix exists. So you give the prefix and you take the temp, right, as this, and then you go on search for this prefix in this particular try block, right? Try data structure. So how are we searching? So first character, if you have a pointer for that, then you go for the next pointer. But if you don't have it any prefix, right, what you are going to say, okay, if it is null, you are going to return a false. That means that prefix is not existing. So similarly, if you go back, right, so if you say prefix of OP, right, prefix of OP, so what we are saying is the prefix is OP. We are searching for OP, right? So we get the data structure for try, and then prefix is first character is O. So first character's child pointer is not null because O is already existing. Good. So it will take the child pointer of O. So O is existing, right? Good. And next, when we move further, right, we are at P. So for O, do you have a P pointer, right? For O, do we have a P pointer? O has only pointer A and pointer N, right? We don't have a P pointer. That means we are going to return a false, right? Simply. So that's how this prefix search is going to work. Once you exhaust through all the characters, right, that means you are going to return true because that prefix is existing in the try data structure. If somewhere the prefix is not existing, you are going to return false. So this is the prefix search that we are going to use in our algorithm, right? So coming to the algorithm to solve this particular problem, right? So what we are going to do is we will start our search with each character, starting with each character, right? So we'll start our search with O, A, N, E, T, A, E, all these starting places. But we will make sure before starting, what we are going to do is we will make sure if you have any words starting with those characters. So at O, yes, we have one word, so we will go further. But at A, when we are starting our search starting with A, right? Starting with A, do we have any word starting with A? No. So we don't have to go further. Do we have, this is A again, we don't have to go further. This is N, we don't have to go further. This is E, yes, we have a word starting with E, so we go further. Do we have starting with T? No. A we don't have. E we have, we go further. I again we don't have. H no, don't have. K, R we have. So likewise, whenever we search through the prefix tree, right, if we get the answer saying the prefix is available, then we go further, otherwise we don't go further. So that is a simple logic. So at a given cell, we will be going through 4 different directions, right? So adjacency is 4 different directions, right? So if you have I, J as a cell, right? If you have a cell at I, J, right? So what are the adjacent things, right? I plus 1 J, right? I minus 1 J, I, J plus 1, I, J minus 1, right? So what is this I plus 1 J means? This is a character in the next row, that means down, right? And this one is up, and this one is right, and this one is left, right? So that's how, these are the 4 directions you can move, right? So adjacency is they should be either horizontally connected or vertically connected. So horizontally connected means we are going left and right. Vertically connected, we are going up and down, right? So those are the 4 different directions we will be going, right? And while we go through that, right, we will accumulate those characters and check if you have those words existing in your prefix tree or a try, right? So that's how we are going to go through. So let's go ahead and look at the code for this and understand more in that way. So we already saw the try class. We will go through the solution now. So initialize the try class, initialize number of rows and number of columns, m and n basically. So even though this example is 4 by 4, it is not guaranteed that the number of rows and number of columns will be equal, right? Because it is a 2-dimensional board. It did not say 2-dimensional square board, right? So since it said 2D board, it could be rectangular board also. That's why I have m and n as distinct. And I have a hash set of things that we are going to find, right? And the visited array, this is a Boolean array where we are going to mark those particular cells as visited or not. So get the m and n, the number of rows and number of columns in the board, and what we are going to do is, whatever the words that are given in the words, right, we are going to insert into the try. This is the try class that we declared. First we insert into the try, right? So once you insert into the try is ready with all the words that are given. It is ready to do the prefix searching, right? Good. So now what we are going to do is, we are going through all the board, right? All the board with every starting point. So I is equal to 0 to m, j is equal to 0 to n, basically through all the board. So this basically reset visited. So this will be resetting the visited array for each of the starting points. So traverse board. So we are going to traverse through the board for starting with I and j, basically the cell, right? ith row, jth column, right? And obviously, since we are starting, we are giving a new string builder to accumulate the stuff, right? So, and revisited is simple. Basically, it is going to initialize everything to false to start with, right? And traverse board is the doing heavy lifting, right? So what we are doing is check. Basically, the I and j are within the bounds here, right? It should be greater than or equal to 0, and it should be less than m and n respectively, right? And it should be not visited. The cell should be not visited. If so, then only we want to visit again, because it said the same letter may not be used more than once in a word. That's what it is. So we should not use the same letter more than once. That's why we want to make sure we visit only once. So if it is not visited, then only we are going forward. If it is visited, we are done. So visited, I am marking it as true, right? And then I am appending the current character to the string builder. Once you append, check if that prefix is existing in your try. If it is existing, then you go further. If it is not existing, you don't go further. Understood? Simple. That's what is the logic that we said, right? If it is existing, we go further. If it is not existing, we don't go further, we exit. So as we said, if it is existing, we will make sure if it is a word, if it is a complete word, if it is a complete word, if it is a complete word, you add it to the answer list, right? If it is a complete word, that is what the search method is going to give us. So if it is a complete word, then we add it to the answer. And now what we said is, we are going to traverse through 4 different directions, right? Down, up, right and left. So that's what we will be doing. Traverse the board. So this is I plus 1 j. What is this? Down, right? And I minus 1 j. This is up. I j plus 1. This is right. I j minus 1. This is left. So these 4 different directions we are traversing. And while you traverse, you adjust your string builder. Once this traversal is done, you remove those characters, whatever you have accumulated so far. That's what I have been doing here, right? So that's what will be done. So what does it essentially do is, you go through the 4 directions and check if that particular prefix is existing in the prefix array. If so, you continue the search. Otherwise, you don't continue the search, you come back, right? So wherever your search function returns, okay, this word is existing, you add those words into the answer list. So that is what your traverse board is going to see. Finally, once you go through that, right, your answer list, whatever you accumulated, you are going to return. So again, majority of the work is done in the prefix exist and search, right? So you are searching for a particular word and you are searching for a particular prefix in the try data structure. And this traverse board is essentially doing only spanning across 4 different directions starting from wherever you are, right? So this is only a facilitator, and majority of the work is happening in the prefix exist and search methods, right? Good. So that's how we are able to solve this particular problem. Let's go ahead and look at the time and space complexity for this. So how much time we will take, right? So here we are going through each word, right, and searching through, inserting that word into try data structure, right? So since we know only the number of words, let's say there are p number of words, right? P number of words. That means this for loop is going to take order of p, right? Order of p. But each word we are going to take some time to insert, right? So how much time insert method will take in general? It will be taking equal to the word length, right? So the words are given with variable length. Since we don't know, let's assume L is the average length, right? L is average length of word. That's what we will say. So in that particular case, we will say order of p into L, right? So that is the time complexity for this for loop, just to insert into the try. And after that, what we are doing is we go through each cell, right? And we go further only for those characters or those prefixes where they are existing in this word, right? So obviously this will take order of m into n, right? So plus order of m into n. And if you go through the traverse board, right, how much traverse board is spanning across, right? It's going through all the cells at most once, right? It's going through all the cells at most once, because we are making sure visited is marked to true once it is visited. But how many cells are there? M into n, right? So that is being captured anyway, right? So m into n times we are going through the traverse board function, right? But into we want to have some constants, right, which we don't know. That will be obviously again the length of the word, right? We will say L, right? Order of m into n into L, because we don't know the length of the word. So total complexity for this will be order of m into n into average length plus order of p into L, right? So this is the total complexity. So it's not easy to come up with the complexity for this kind of problems, because the word lengths and number of words are unknown to us. That's why we assumed there are p number of words and L is the average length. That's why we came up with this particular time complexity. So what is the space complexity? Are we using any space here? Yes, we are using a space for the try, we are using the space for the returning the answer, we are using the space for visited. So visited will be order of m into n, that will be easy to say, right? Because that's what we are using. Plus how much space we are using for the answer, it will be probably equal to the length of the words, right? So that will be anyway order of p into L, that's what we will say, right? Because p is the number of words and L is the average length, so that is the space. Plus we are using the try, right? So how many spaces we need for try to generate a try? That actually depends on how many levels that we have in the try and how many characters individually that we have, right? So again, it will not be easy for us to get space complexity for the try, because we don't know the number of words and their average length and how coherent and how duplicated the data is, right? So for that particular purpose, we will say again order of p into L. So this is the space complexity for this particular algorithm, right? So if you have any further questions, please post them in the comment section below this video. I'll get back to you as soon as I can. I would like to remind again, please go through the try video once more so that you will understand this particular problem in a big way, right? So I have posted this code to the GitHub repository. You can find the link in the description below this video. If you haven't subscribed to the channel, please go ahead and subscribe and share among your friends. Please click on the bell icon so that you will be notified about all my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe and goodbye.